Good evening, my dear J Warriors. Welcome to the J Booster 2026 series for your January attempt. This is your Captain Shreyas, and today in this rotational motion, quick one shot, I am going to cover the following things which are very important from exam point of view. Okay, we are not here to focus in that 2 year or 3 year preparatory mode. We are right now in the final mode, the beast mode, you can call it, right? We are going to discuss moment of inertia, the two important theorems, right? Then the pulleys with masses with torque and rotational energy, and finally the conservation of angular momentum. These are those topics which I have personally seen along with my team are constantly getting repeated year after year. So these topics in the chapter of rotation and rigid body, you must be very, very clear of. All right. Hi STK, hi Hanshika, welcome Rio, welcome. J 2027 aspirant, I want to clear my backlog. Can I watch this lecture? Please tell me. Yes, definitely you can clear your backlogs, STK. But please let me tell you that if you want those long form videos where I have gone lecture by lecture, then you can go to the home page. It is there right over here, the old playlists, okay, the nurture playlist, or even this playlist, or even the last year's roar series which we had conducted on the channel. That also you can watch. That is the long format videos which every chapter takes around 5 6 hours, 8 hours, 10 hours, depending on how big it is. So those things you can watch. Today I'll be doing only the high weightage parts in 3 hours, because you obviously rotation is a big one, right? Hi, good evening, good evening. All right, so let's begin with the class, and I hope everybody is ready, geared up for the session. And yes, let's start. So by the way, the first thing that we are going to start off with is moment of inertia. Now, what is this moment of inertia? If you just ask me what is inertia, then inertia is nothing but resistance to, or basically you are not willing to change your state. So inertia is nothing but resistance to change the motion. If you are at rest, you want to move. If you are moving, you want to turn. If you are turning, you want to stop, whatever. So any kind of changes which occur during motion, you are not so open to it. So that is that property which is inertia. And inertia is measured by mass, right? If more mass is there, more difficult it is for it to set into motion or to stop it and stuff like that. Now, what is this moment of inertia? It is just like inertia which you have studied, like mass, but in rotation. Analogous means similarity. So analogous means just like how it is here, same thing it is over here. So it is easier to understand. So in rotation, the property which will resist any change of rotational motion, that is called moment of inertia. Like for example, there is a giant wheel. To set it into motion, obviously you will take some time, you have to apply some forces and all of that. So it will resist. If the giant wheel had more people, or if the giant wheel size was different, or if the giant wheel was made of different material, so you will see the resistance to change the state will be different. Even a wheel, a top, or a fan made of different size, different mass, different length, dimension will offer different resistances to rotate. That is measured by moment of inertia. Now, before going to big bodies like a giant wheel or a disc or a top or a sphere or a globe or a fan or whatever, we start with a simple particle. Imagine there is this particle and it has to go around this particular axis. It has to go around this particular axis. It will obviously offer some resistance if that same particle was here versus here versus here versus how much the mass is versus which axis it is. If the axis was not like this, if the axis was like this, or if the axis was like this, the resistance which that mass will offer, meaning to move it around, how difficult it is, the difficulty experienced will be different. So that is what moment of inertia is. and we start off by a particle. Okay, we start off by a particle. Hi Jayakumar, hi Pratik, good evening. Hi Jay Aspirant, great Indian, welcome aboard. Yeah, all right. You want to join as an intern? I think we have posted as a posted an opening today for the script writers and all of that. So you can just check it out. It's there on the community. So there are some openings there. In fact, some students also have joined us, and there are many students who have graduated and also come back to us as product and all of that. So guys, we would love to have you. Okay. Anyways, so what is the moment of inertia formula for a point mass? It is how much mass it is into distance square. Mass into basically r square. Is that absolutely clear, my dear warriors? Yeah, m into r square. If more mass is there, more difficult. R is more, that means you have to take that particle from a lengthy path, far away point from the axis, then also it is difficult. But that same mass, if it is close, then it will be easier. Yes, it is scalar, and the unit is, because this is kg into meter square, unit will be kg meter square. Unit will be nothing but kg meter square. Is that okay? So simple mass going around an axis at a distance r has a moment of inertia I. I is the symbol of moment of inertia, which is m into r square. Now, sir, what if there are more particles? It is very obvious for you to think now. This is the moment of inertia of a particle. One more is there, one more is there, one more is there. Many particles are there. Then you will have multiple terms. First mass into first distance square. Second mass into second distance square. Third mass into third distance square. If you add them up, the sum of mr square will give me, the sum of mr square will give me the total moment of inertia of this multiple particle system. Think of it like a Christmas tree with some masses attached, and that Christmas tree or whatever that tree is rotating with different masses present everywhere. So the moment of inertia of such a thing will be summation of mr square. Okay, I hope this is absolutely clear. And moment of inertia, unlike mass, has to be defined with respect to an axis only. Like mass, I can just say, what is a mass? You'll say 5 kg. What is that mass? Yeah, it is 50 kg. But you cannot ask what is that thing's moment of inertia, because you need to tell me about which axis you are rotating. Because if you change the axis now, then the moment of inertia value only will change. Getting my point? Yeah. Why r square comes? There is a derivation for it. In fact, I have done that derivation in that long-term videos and all of that. It comes via derivation. Okay. So it's not like magical. Why not cube? Why not square root? Very valid question. Why is it squared? There is a derivation for the formula of moment of inertia. It comes via comparing and all of that. If you watch Road series or my older videos, you will definitely get it. Okay, Katir? It comes from that particular thing. I hope this is clear. Great. Shall we move ahead? Okay. Hi, Mohammed. Welcome aboard. Yeah, you can check those older videos right over here. Go to the homepage. You can see these one-shot preparations, this physics playlist, or you can go to class 11th preparation. Okay, over here, and in that nurture series is there. You can check that videos out. Detailed classes are there. Okay, cool. Yeah, right over here. Oh, where did it go? Here. This nurture class. Okay, this is 11th. For 12th, this is the one. All right. Okay. Now, moving ahead. If I ask you a simple question, there are two disks with me. One is having a radius r, the other is having a mass of 2m, sorry. Both radius are same, but masses are different. Which one will stop first if both of them were rotating with the same speed? One has more mass, one has less mass, radius are same. So it's quite obvious that the one with more mass will take more time because it has larger momentum, it has larger energy stored within it. So to suck that energy out, it will take longer time. So this disk will obviously be more difficult for me to stop. Does that make sense? Yeah, the second one. Yeah, very good. Next, if I ask you, masses are same, but the radius are different, then which disk will take more time to stop? Now, this is a very funny example why I'm giving you, because a lot of people think moment of inertia is just mass. Wrong. Even if the masses are same, they both will give me different difficulty in stopping them. That means different moment of inertia, different resistance also. Reason is, in this particular disk, being of bigger size, the masses are very far away as compared to being closer to the axis. So as a result, what happens when the masses are far and it is rotating? Just visualize. If masses are close, it's going in small circles, less energy, less speeds. Masses are far away, they are going in big circles and they have more energy. So it will be more difficult for me to stop the masses moving in big circles with larger speeds, having larger energy, larger momentum. So this will offer more resistance. So it is not just the mass alone which decides the moment of inertia, and it is also how far these masses are. That's why R comes into the picture. Okay, if the masses are far away, it is more difficult for me to stop such a rotating body. So moment of inertia definitely depends on the mass and how that body is, how big or small that particular body is. So you might now wonder, sir, can we actually calculate the moment of inertia of this disk? The answer is yes. There is a simple formula. Instead of summation, now you use integration. When you had point masses m1, m2, m3, m4, m5, and these masses were rotating, then you just did summation of mr square, each mass into distance square. But when you have a disk-like object or a plate or a sphere or a triangle or a cylinder or a cone, whatever, then how many masses will you take? M1 R1 square, M2 R2 square. You can break it down into infinitely many particles. So that summation will convert into integration. So when there are continuous bodies like a sphere, a cone, a plate, a rod, or something like that, then you divide that body into infinitely small masses. Each infinitely small mass is dm. So dm into that distance square, another dm into r square, another dm into r square. So you keep doing that again and again till you complete all the masses in that particular body. So that becomes then the integration. So dm into r square integration gives me the moment of inertia of such a body. Okay, I hope this is clear. Awesome, awesome. Thank you so much, the guy. Okay. Uh, Video lectures, Suren. Then is it just send me a video of whatever is not working or working, okay, on Telegram, Captain Shreyas. I will post it to the concerned team. Okay, Captain Shreyas. Okay. Now, sir, you are telling me this integration is there. So, do I have to do this integration again and again? The answer is you don't have to. The integration is already done as a part of the physics derivations in your textbooks. You just have to remember the final result from the mains perspective. Many students also wonder, what is the use of calculating this moment of inertia? So why do you start with this? The answer will come very soon when you learn torque and angular momentum. There you will need the value of I, just like you need mass in normal force and momentum and all of that. Same way, you will need the value of moment of inertia in many places, and there you will have to know the value immediately. So that's why we do not perform this integration again and again. For standard bodies, we rather remember it for direct application. Now there are only certain standard bodies which you need to remember. Okay, so let's see what they are. But just keep this in mind. Again, I'll repeat this. Moment of inertia finally depends on not just the mass, but also it depends on what kind of shape and size it has. So more mass will obviously have more inertia, but it also depends on where that mass is located. That means how it is distributed, what is the shape of the body, all of that, and also the axis of rotation. If the axis will change, then the masses will rotate in different circles. Each mass will rotate in different circles about this axis versus this axis versus this axis. So the axis also plays a very major role. Okay, sir. So what are the formulas of moment of inertia, sir, which have to be directly remembered without integration? Without actually doing the integration every time? The answers are as follows. First, start with a ring. Moment of inertia of a ring when you rotate it about the central axis like this. Okay. then the moment of inertia of such a thing is given by just mass of the ring into radius of the ring square, just simply mr square. If you take a disk, that means a thin sheet which has been cut out, or just a disk, a CD disk or whatever, okay, then the formula is m into r square divided by 2. Mr square whole thing divided by 2. So for ring mr square, for disk it is mr square by 2. Keep this in mind. Now there is a cylinder, but the cylinder can be of two types. One is a hollow cylinder, other one is a solid cylinder. Hollow means like a pipe. Inside a pipe it is hollow. Solid means like a pen, you cut it, or a rod. Okay, you can think it's like a cylinder which is filled with some material. Okay, or a pipe which is filled with water. That's like a solid cylinder. You can think of it. In this case, the formulas are identical to that of a ring and a disc. For a ring, it is mr square. For a hollow cylinder, also it is mr square. For a disc, it is mr square by 2. For solid cylinder also, about the central axis, when you rotate it, it is mr square by 2. Now you might wonder, is this just by coincidence? What do you think? Is this coincidence? Yes or no? Yeah, I'll be doing problems also, Katir. Yep. Yeah. Is this just a coincidence? No, it is not a coincidence. The answer is, actually, if you take this ring, or in fact any geometry, if you take the 2D version and you elongate it and make the 3D version, the formula remains the same. Yeah, very, very useful trick for many questions. If you take any 2D geometry and you pull it, stretch it, and make it into a 3-dimensional geometry, so you can visualize, if you make this into a 3-dimensional geometry, inside part will be hollow. If you stretch this and you make it into a 3D geometry, inside part will be solid. So it will become a solid cylinder. So, my dear students, the formula remains the same for such stretched bodies which are converted from 2D into 3D. Okay, very, very simple. And the reason for that is, when you stretch it, the mass is the same, the axis is the same, and how far the masses are, that means the distribution, that is also the same. So that is the reason why the formula does not change, because I just told you about it, that moment of inertia depends on axis, the shape, size, and the distribution and the mass itself. So the mass is not changing, the axis is not changing, and even how far, because if this mass is here, when you stretch it, that mass is just pulled here, but from the axis it is at still the same distance only. So it will not change. So moment of inertia also will not change. So for a solid cylinder, mr square by 2, hollow cylinder, just mr square. Okay. Last two geometries, and then there is one more geometry, I'll come to it, is hollow sphere versus a solid sphere. For a hollow, it is 2 by 3. For a solid, it is 2 by 5, mr square. Now, sometimes you might get confused. So 2 by 3, 2 by 5, just if I get confused, how do I remember it? Okay, I'll give you a hint. For a hollow cylinder, for the same mass and radius, if you compare it with solid, in hollow, inside part is empty, so all the masses are on the circumference, on the shell, on the outermost surface. So the masses are far away. If the masses are far away, the moment of inertia will be higher. But for a solid sphere, inside is full, so the masses are now closer to the axis. So if the mass is close to the axis, r will be less, moment of inertia will be less. So 2 by 5 is less than 2 by 3. 2 by 5 is 0.4, 2 by 3 is 0.67. So obviously 0.67 is more than 0.2. So hence you can see for a hollow cylinder, moment of inertia for same mass and radius is higher as compared to a solid sphere whose moment of inertia is 2 by 5 mr square. Okay, absolutely clear, my dear warriors? Yeah. CR7, this is not whole syllabus, and this is not your that detailed class which you are doing. This is a mini series which you are doing in the month of November to make sure we cover important high weightage chapters and their topics, so that it boosts your score and you get set go, and also focus on those topics, so that that will only give you marks. Other topics will waste your time. It will be very interesting, but it will not give you marks. So right now what is important is marks, not learning, because unfortunately we have less time. If you had come to me 2 years back, 1 year back, I would happily, like I have been teaching in my long-term batches, I teach very coolly, very smoothly, very, part by part, we are going coolly. But now we don't have that much time. I hope you get it. Okay, right. I hope CR7 that is clear. All right, Kathir. Okay, clear, my dear captain. Awesome. Now there is one more geometry which you should know, and that is basically the rod. And this is also going to be very important in solving many questions. So if you have a rod, basically, this is a rod, and the axis of rotation is the central axis like this. Okay, the axis of rotation is basically the central axis, and the mass of the rod is m, and the length of the rod is, let's say, L. Then the moment of inertia of such a rod is given by mass into square of the length divided by 12. Very, very important when you rotate it about the central axis. ml square divided by 12. That is the formula which you should know for a rod. Great. So let's say, for example, I give you a question to start off with. It's a very nice question. And if I tell you, if if a sphere, if a solid sphere rather, if a solid sphere has moment of inertia given as I, then the moment of inertia of a solid sphere of a solid sphere of 2r radius of 2r radius and of 2r radius and same material is how much, and same material is how much? That is the question. So let's try and solve this. Okay, not a big deal, easily we can do it. Let's see how do we approach. Solid sphere is their original moment of inertia is it is I, and for a solid sphere the formula is given by 2 by 5 m into r square. Now I want to figure out what is the new moment of inertia, but when the radius is now how much? 2r over there. So a lot of people do this common mistake and they write this 2 square is 4. So they just put number 4 here. 2 by 5 mr square is I. So they think the answer is 4 times of I. But this is not the right answer. That is the problem. A lot of people do this mistake. Yes, you have to take the radius as 2 times of r, undoubtedly. But a lot of people make this mistake of putting the mass as m. That is wrong. This mass will also be the new mass. You might then start struggling to think, why is it new mass? What has changed exactly? Do not forget, the sphere is of 2r. Nowhere did they mention mass is same. Oh sir, then how do I find the mass? So they left a hint somewhere. Of the same material. Same material means the matter is the same, the compound is the same, the element is the same. That means density is the same. So that is the catch in this particular problem. Same material means density, and density is mass by volume. So volume is 4 by 3 pi r cube originally, solid sphere's volume. Second time the mass is new mass, the radius is new radius. So it is 4 by 3 pi 2r and then whole cube. Now a lot of things will obviously get cancelled, like 4 by 3 pi everywhere. So you will be left with m is equal to my new mass and 2 cube over here, because r cube and r cube has got cancelled. So therefore my new mass will be 2 cube multiplied by m. 2 cube is 8, so 8 times of m. So that is the thing over here. So it is 8 times. So this will become 2 by 5 multiplied by 8m. 2 square is 4. So 4 multiplied by r square. 8 4s are 32. So 32 multiplied by 2 by 5 times of mr square. So that is 32 multiplied by 2 by 5 mr square is nothing but I. So 32I. So the new moment of inertia. So the new moment of inertia is 32 times of the old inertia. That is the final answer. Got it? So it is not double the mass. Lot of people think the mass will also double because radius has doubled. Guys, how is it possible? Come on, you have to think a little bit more maturely. Okay, it's a solid sphere, completely filled with solid material. So if the radius doubles, so volume will also become 8 times. So mass will become 8 times because volume of a sphere depends on cube of the radius. Cool? That is the catch in this question. A similar question can be also asked, let's say, just with the particles themselves. Say this was also a very common kind of question where it was given to us that, let's say, there is a mass of m and then there is a mass of 3m and it is rotating about an axis which passes through the center of mass. It passes through an axis which rotates about the center of mass, and it was also mentioned that the total distance is basically r, like this, from the masses themselves. Question is, find the moment of inertia about the axis through through the center of mass. About the axis through the center of mass. That is the question. Now, the problem over here is that I really don't know how far is this, how much is this R1, and I do not know how much is this R2. Because only then I can actually figure out what the inertia is. I know the moment of inertia is there are two masses, so there will be two terms of mr square. This mass into this square, this mass into this square. All distances have to be measured from the axis of rotation. So the mass is m, distance is r1. The second mass is 3m. Distance is basically how much? It is r2, so r2 square. The problem is I do not know what is r1 and r2. Can't leave the answer like that. I have to somehow compose it in terms of r. So how do I write it in terms of r? Let's see. First of all, what I will do, I'll go back to the chapter of center of mass and I'll start thinking. To find center of mass, what do we used to do? Yeah, we used to take some origin, we used to take x and y axis and then write down the formula. So if I take this as my y axis and this as my x axis, you can see the center of mass is definitely at the origin. The center of mass is definitely at the origin. So using the formula, XCOM is M1 X1 plus M2 X2 whole thing divided by M1 plus M2. Notice what happens. The x coordinate of the center of mass will be 0 because I have chosen my x and y axis itself such that the origin is at center of mass. What is M1? It is M. What is R1? X1. X coordinate is minus R1. So you have to put it with the sign because this is proper vector equation or coordinates. Second mass is 3m. X2 is basically positive R2 because this mass is at a distance of plus R2 coordinate. Upon some mass, which is, I don't care because anyways it's in the denominator, it will not matter. Take this guy over here. So you will get m into R1 is equal to 3m into R2. Therefore, you will get R1 is equal to 3 times of R2. But that is not enough for me to solve the problem. I will do one more thing. The total distance is R. So I need it in terms of R. And I know R1 plus R2 is basically R. So what is R1? It is 3 times of R2. R2 is just R2 only. So therefore, 4 times of R2 is R. Therefore, R2 is nothing but R by 4. Not just that, we can also write now R1 how much it is. It is 3 times of R2, R2 being just R by 4. So now these are the two values which I'll substitute over here to get my final answer. So m into R1 square, that means 3R by 4 whole square plus 3m into R2 square, that means R by 4 whole square. So this will be nothing but 3 square is 9. So 9mr square divided by 16 plus 3mr square by 16 right over here. Okay, 9 plus 3, that is going to be 12. So 12 mr square by 16. 12 goes with 4 3 times. So 3 mr square. 4 goes with 16 4 times. So 3 by 4 mr square is the final answer. 3 by 4 mr square is our final answer. Is this absolutely clear, my dear students? Very good. Excellent day. Okay. Okay. Uh, Shreyas, wow, you are with my name. If you are starting from the scratch, then I would advise you not to watch this video, because this will be for those students who have done at least some board level, or maybe you have done some time this particular chapter and you are kind of revising, then it is good. And you are forgotten the chapter, you have done it sometime, then it is good. But if you have not done it anytime, then I would strictly advise you to check out this particular video of mine, where I have taught everything in detail, like for example, this nurture playlist, or even this uh, roar playlist also you can take. So here I have done it. So if you go down over here, you will see it. Center of mass, momentum, collision, rotational motion, 4 hours for 50 minutes. So almost 5 hours I have taken just rotation. Okay. So this is one lecture you can watch, or else you have this particular series where I have taught it in detail. You can see over here. Yeah. Just open this playlist. Oops, not this one. Units and dimensions, but yeah, you can just go down over there and you will see it. Okay, so you can just go down over here and you will start seeing it. Current, electricity, okay, all vectors is there. So you can see each lecture has been taken like 3-4 each chapter has been divided into 3-4 lectures and all of that. So you can see that right over here, Newton's laws. Okay, slowly I have taught the chapter. So if you want that, you can go down into this particular playlist. It's a huge playlist, guys. Okay, all right. Okay, perfect. Oh, this is your official name only. Okay, okay. I thought you are my fan or something, because a lot of people come with my name. So Mr. Captain, Mr. Capto is there, Pandu is there, Champa is there, Mr. Shreyas fan is there, Shreyas Sir fan club, one student is there. So sometimes I need to ask. Okay, but I'm glad that you have my name. Okay, now going ahead to the next concept in moment of inertia, and that is the two important theorems which is used to calculate the moment of inertia about a non-standard axis. See, the formulas which I just gave you, they are all about the central standard axis. Like the rod is about the central axis, the spheres are about the central axis, the cylinders, the rings, all central. What if you rotate the ring about the diameter? What if you spin the uh, disc about the circumference? There is one line over here. What if you take some other axis over here, or the axis outside, or what about the end? You are taking the rod and spinning it about the end. So then the moment of inertia will be completely different, and that is the reason why we have two important theorems which helps us identify those values. One is perpendicular axis, the second is parallel axis theorem. They are very simple and straightforward, but there are some conditions. What are those conditions? Keep this in mind. Perpendicular axis theorem is only valid for planar bodies. Yes, planar bodies. It is only valid for planar 2D laminar bodies. So I have put that note over here. I think it is not visible, but in the PDF it will be visible, because this toolbox has come. I can't get rid of it. So, my dear students, it is only valid for 2D objects. So, what are those 2D objects? Ring, yes. Disc, yes. Triangle, yes. Sheet, yes. A rectangle, yes. Sir, cylinder, no. It is a three-dimensional object. Solid cylinder, no. Solid sphere, no. Hollow sphere, no. Cone, no. So, all these bodies you cannot apply, but only two-dimensional planar bodies you can apply. But there is no such restriction for parallel axis theorem. Parallel to, you can use it for any kind of body, 2D, 1D, 3D, 4D, whatever you want, you can use it. Okay. So the main restriction comes in perpendicular axis theorem, where you can only apply it for laminar planar 2D objects only. The restriction in parallel axis theorem comes in another way, that one of the axes must necessarily pass through the center of mass in order to find the moment of inertia about some other axis. So the restriction in parallel axis theorem is one of the axes should pass through the center of mass of the body. But here there is no such restriction of center of mass. The axis will be somewhere. But you will see in perpendicular axis theorem, there will be three axes which will be involved, out of which two's moment of inertia you should know or you will know, and the third one you will find out. So two moment of inertias you will know, one you will find out, okay, based on the other two's knowledge. How? I'll show it to you. But let's say you are taking this axis and this axis, and the moment of inertia when you rotate about x-axis and let's say y-axis, which are in the plane of the body, 2D plane, is ix and iy. If you add them, then if you take an axis which is perpendicular passing through their intersection, and if you rotate it about this axis, this body, the moment of inertia is Iz, which is just the sum of Ix and Iy. So these are the moment of inertias about the perpendicular axis, which are in the plane of the body. Their sum is the result, which will give you the moment of inertia of an axis perpendicular to the plane of the body. As simple as that. So Ix plus Iy is I perpendicular or Iz. You don't have to remember Z, Xy. Just remember it this way. You add the moment of inertias about two axes which are in the plane of the body. You will get the moment of inertia about an axis perpendicular to the plane of the body. To give you a simple example about this, let's take a ring or a disc, or it doesn't matter. Okay. So let's say we take a disc for now. Okay. It's a simple disk. This is a disk. And I want to figure out what is the moment of inertia about an axis which is basically in this particular direction. I want to figure this out. Okay, I want to find this. I will call this I. Now the problem is, in order to find this I don't know any standard formula. But I know one thing. If I use some kind of symmetry over here, I know if I draw one more diameter, and if I try to rotate it about that diameter, if this is I, this also has to be I because of symmetry. In fact, any diameter I take and I rotate it, the moment of inertia will still be equal to I only. That acts like an advantage because now I have a two-dimensional object, which is a disk, and I have two perpendicular axes which are in the plane of the disk. So all I need is now a third axis which is perpendicular to it. And that would be obviously like this. And this axis moment of inertia, which is in the perpendicular direction, is something which I already know to be mr square divided by 2, which is nothing but mr square divided by 2. And now using perpendicular axis theorem, this I perpendicular will be moment of inertia in one direction, moment of inertia in the another direction, both to be in the same plane as that of the object. Otherwise, even this and this is in the same plane, but this is perpendicular to it. So the one which is perpendicular will be on the one side, the other two which are in the plane of the body will be on the another side of the equal to symbol. So this I perpendicular, well, I know what this is. This is nothing but mr square by 2, and I plus I is nothing but equal to 2 times of I. Therefore, I will be equal to mr square by 4. mr square by 4. Very good. I hope this is absolutely clear. Everybody with me? Very nice. Amazing, amazing. Now, same way, now that we have understood how to use perpendicular axis theorem, let's also understand how do we use parallel axis theorem. Parallel axis theorem. Okay. How do we use parallel axis theorem? And what is parallel axis theorem? First, number one, there should be an axis, like I said, which passes necessarily through the center of mass. You have another axis which might be through the body, outside the body, on the edge of the body, doesn't matter. But it must be parallel to this axis. That's why the name only has come parallel. In the previous thing, it was perpendicular. That's why the name was perpendicular axis theorem. Here, the axis is parallel. That's why the name is parallel axis theorem. So the moment of inertia about that new parallel axis, this is that new parallel axis, okay, is given by the old moment of inertia about the center of mass. So moment of inertia about this axis plus the mass of the entire object into d square, meaning how much distance do you shift that axis by. So this moment of inertia plus mass into the shift square is the new moment of inertia. Let's apply it so that you guys get an idea about it. Say for example, I tell you that listen, you have to figure out the moment of inertia. What is this? 1 second, guys. The board is not working. I don't know. This has been happening frequently these days, especially after the new Windows update. Okay. Hmm. Okay. So imagine I have a ring like this, and I will take, let's say, an axis over here, or even this is, oh, by the way, this is even valid for three-dimensional objects. So let me take a three-dimensional object so that you are convinced. Okay, so this is a three-dimensional object, like say for example a hollow sphere, and you have taken an axis over here. So this is hollow sphere. This is hollow sphere. The question is, what is the moment of inertia about this axis? What is the moment of inertia about this particular axis? How do we figure this out? First of all, if I just take my normal hollow sphere, I usually will know the moment of inertia about this axis, and that axis will pass through the center of mass, and the moment of inertia through the center of mass for a hollow sphere is 2/3 mr square. Isn't it right? Now I am to shift it by some distance. As you can see, I am shifting it by distance of radius itself. So the new moment of inertia about the parallel axis is center of mass's moment of inertia plus mass multiplied by how much ever shift you undergo, square of it. So what is the moment of inertia about the center of mass? That is nothing but 2 by 3 mr square. Shift, how much is the shift? It is basically r, so mr square. So 2/3 plus 1 is basically 5/3. So 5 by 3 mr square is the required moment of inertia about the fresh new axis. Yeah, everyone? Okay. Yes. J26-27 series, no, not the entire one. Few chapters are remaining. We'll try to complete it if possible. But because the exam is close by, that's why I started with this series. Okay. We'll try to do it, my dear. Okay. Now, if you take a rod also, this is valid, and this is more important because many times you will find this necessary. So imagine you want to find the moment of inertia about the end of the rod. That will be equal to moment of inertia about the center of mass plus mass into how much ever shift you undergo. In order to shift the axis from center of mass to here, that shift is obviously L by 2. That shift is obviously L by 2. This is for the rod, and this is center of mass of the rod. So let's try to do this and see how much do we get. About the center of mass, I just told you it is ml square by 12. Shift is nothing but L by 2. So square it. So it will become ml square by 12 plus ml square by 4, which gives me ml square by 3. You can do the math. It's not that difficult, but still if you want it, it will be ml square plus 4 goes with 12 three times. So 3 ml square by 12. 3 plus 1 is 4. So 4 ml square by 12, and 12 goes with 4 three times. So ml square divided by 3. So that is the answer about the end, that is ml square by 3. Very, very important. No problem, Cedric. Okay. Great. Great. Okay. So let's do some questions. This is a match the following question. Let's see if you can solve this. We have some objects and their axis given. You have to figure out who will be the correct moment of inertia. For example, moment of inertia of a solid sphere of radius r about any tangent. Moment of inertia of hollow sphere r about any tangent. Moment of inertia of circular ring of radius r about any diameter. Moment of inertia of disk about any diameter. I think couple of them we just saw. Like I'll tell you which and all. See this one. Moment of inertia of a hollow sphere about any tangent. That is basically this problem only. Hollow sphere. This is a hollow sphere and this is a tangent drawn, and we figured it out. It was 5/3 mr square. So exactly that only. So basically 5/3 mr square is right over here. I can see. So B is going with 1. B is going with 1, I think only in two places, over here and over here. Naturally, this option and D option will get ruled out because only those matching I will take. Other options I don't even have to check. One more thing which we solved, I think, was the disk about the diameter. So check this particular bit out. About a circular disk about any diameter. When I explained you perpendicular axis theorem, this was nothing but a disk, okay, and this was the diametrical axis about which we had to figure out the moment of inertia, and we figured it out to be mr square by 4. So why not use the same thing over here? Mr square by 4, mr square by 4, yeah, 1/4 mr square. So D option is going with 3. D option is going with 4 here, D is going with 3. So automatically this will get ruled out. Hence option A must be the right answer. This is how you are going to solve in the exam. You don't have to solve all the 4 options in match the following. Usually 2 options are more than enough. Is that clear, my dear students? Everybody? Pakka? Great. Awesome. Awesome. Very nice. So our correct answer is nothing but A. But still, if you want to check, A is going with 2. Moment of inertia of solid sphere about any tangent. A is going with 2. Yeah, 7/5. It is correct only. Like, say for example, if we take solid sphere about any tangent, then this is my solid sphere. About the center of mass, it is 2/5 mr square. You shift it, then you get it about the tangent. So plus mr square, which will give me 7. 2 plus 5 is 7. So 7/5 mr square. So which is exactly this option. Same way you can also try it out for something else, like say for example this one. For this circular ring, about its diameter, it will be mr square by 2. Okay, circular ring for the diameter. So you take that ring, okay, this is the diameter, moment of inertia is I, you take another diameter, it will be I. About the central axis, it will be mr square, considering it is just a ring. So I plus I by perpendicular axis theorem will be mr square. So 2I will be mr square. So I will be mr square divided by 2. So that is why this option will go with fourth option, which is also there over here. Okay, perfect. C is going with 4. So option number A is the right answer. Moving on to the next question on your screen, and here it is. Moment of inertia of a square plate of side length L about the axis passing through one of the corners and perpendicular to the plane of the square plate is given by. Plate is given, rectangular plate is given, square plate is given. Interesting, and it is also perpendicular. So how do we do it? First, let me visualize what is exactly the diagram. Okay, so moment of inertia, do I have some space maybe over here? Yeah, okay. So let's say this is my square plate. It is like this. Like this, okay, and the axis is going to be about the corners and perpendicular to the plate of this square. So it is basically this way, something like that, and it is rotating this way. Okay, perfect. So now, okay, till this point absolutely clear. Till this point absolutely clear. Hi KJ Tech, love to see my students from Kerala. Okay, so now what do we do? Now what do we do? Simple. First of all, I do not know any direct formula for a plate. So I will think, can I apply some kind of theorem, parallel or perpendicular axis theorem? If I have to apply parallel axis theorem, I should know the moment of inertia about this central axis, which I don't know. So I get an idea. Maybe I will need perpendicular axis theorem. But for that, I need to know about this axis and this axis, which also I don't know. But with some trick, I think I can find it out. And I'll tell you what that trick is. Just imagine, I just gave you one simple rod. Okay, what is it? A rod whose length is L, mass is M. And I tell you, I'm going to rotate it about the end, about the end axis. What's the moment of inertia formula? Immediately you will say ml square by 3. This ml square by 3, I just got it over here. Just some time back, where did we do for a rod? Yeah, over here. ml square by 3 is the moment of inertia of the rod about the end. So, if this is the moment of inertia of a rod about the end, if I open up the rod and stretch it using our property, it will just become a plate. Visualize this, same axis I'm using. Now it has become a plate instead of a rod. It has become a plate instead of a rod. Okay. And the moment of inertia about this axis, that means the plate is like this, I'm rotating it like this. So this moment of inertia is still going to be ml square by 3. I just told you some time back, like a ring, if you pull it, it becomes a cylinder whose formula is the same. So same property I'm using. Oh, that means if I rotate this plate about this axis, the moment of inertia is ml square by 3. By that logic, if I rotate it about this axis, which is like symmetrical only, it should still be ml square by 3. Now, this is a laminar body. This is a plate, which is a laminar body. And I can use perpendicular axis theorem. And I want to find moment of inertia about this perpendicular axis, which will be, simply put, that ml square by 3 plus this ml square divided by 3, which is going to give me nothing but 2ml square divided by 3. 2ml square divided by 3. Hence, the answer should be exactly that. Okay, 2ml square divided by 3. Is that absolutely clear? So 2ml square divided by 3 is the D option right over here. Clear, my dear warriors? Understood? Perfecto. So the trick was you have to quickly think which theorem you can apply. It felt that both theorems will be like a dead end, but if you think little bit more, then you will realize that a rod can be stretched into a plate. Sir, how do I know rod can be stretched into a plate? How will I even think about it in the exam? Absolutely correct. You can't think about it in the exam. If you have done it before, only then it will come to your head. That is why practice is important. All the surprise elements should be removed. Only then you know that surprise won't remain a surprise. You will be like, I remember, I have done this before. So it becomes easier for you to solve. Yeah, I hope this is interesting question. Hi, Urmila. Welcome aboard, everyone. Yeah, great. Then there is this particular question which had come, which was about two spheres and two masses. At the ends of the light rod, they have been, attached. The distance between the centers of the two spheres is 5 meters. What will be the moment of inertia of the system about a perpendicular rod passing through its midpoint? Okay, so I'll tell you what the question is actually. Two identical spheres of mass 1.5 kg. So one sphere here, and I think the rod is light. Yeah, light rod. So no mass for the rod itself. And the axis though is passing through the midpoint, and it is like this. And the question was, what is the moment of inertia? Now the rod is light, so don't worry about the rod's moment of inertia. Think like this. The total moment of inertia of the system is 2 times the moment of inertia of each of the sphere. Each sphere same mass, same distance, so identical. So 2 times, you take any one sphere, multiply 2 times, you will get the answer. Now the problem is for each sphere also, what happens is, you would generally know the moment of inertia when the axis passes through the center of mass. The problem is the axis is not through the center of mass. It is somewhere here. And usually the formula would have been 2 by 5 mr square. But now you are shifting it by this much amount. You are shifting it by this much amount. So that is the reason why this moment of inertia of the sphere will be 2 by 5 mr square plus mass multiplied by the shift. So whatever that shift is, let's say it is d. So m into d square. That is how you will get the answer. Now 2 2s are 4 by 5 mr square plus 2 times m into d square. Now you just have to substitute all the values over here. For example, mass of each sphere is 1.5 kilos. This is also 1.5 kilos. What about r and d? The radius of each of them is how much? 50 centimeters. So this radius will be 0.5 meters. Now be careful with d now. The shift is from the center to here. The distance between the centers of the spheres is given to be 5 meters. So this shift will be exactly 2.5 meters because center to center distance is given to be 5 meters. So center to the axis will be 2.5 meters. So therefore put this d as 2.5 and you will get the answer. That is what they have also done. And you get the answer as 19.05 kg per meter, kg meter square, sorry, kg meter square. Okay. Logic is clear. How to solve it? This is also a very common model of question. Very common model. Okay. All right. All right. Great. Moving on now to the next concept of basically torque. Okay. Like I said, today we are doing just high weightage important topics which are being repeated in the rotational motion. That is what the focus is. Torque. Let's talk about it. Now, see, a force causes acceleration. A force will cause acceleration of a mass. But in rotation, it is not acceleration which is caused, it is angular acceleration which is caused. Something was at rest, it begins to rotate, speed increases, increases, increases. So what is it that is rotating it? Yes, there is a force, but I won't call the cause of the motion as the force. Rather, it is the force equivalent in rotation or the moment of the force, which has a name called as torque, which is also called as the twisting force. Because just force alone is not enough. Imagine you take something and you hold it very close to the axis and rotate it, versus you have a handle attached to it and then you are applying the same force, which becomes easier. So, same logic when you are applying a force on the door to open it. If the handle of the door is very close to the hinge, it's very difficult to open the door. But that same handle, when it is far away, which is the case, then it is easier for me to pull open that door. So the logic is that, my dear students, that you cannot have just the force to measure how much is the twisting cause or the reason for it to rotate. You also need where that force is being applied so that we can exactly measure the cause of the rotation. So that's why you will see that the manner in which torque has been defined not only has the force but also the point of application of the force. P is the point where you applied the force, O is the axis. So if that point changes, the twisting torque, twisting force will change. The cause of the rotation will change. So just like force causes acceleration, torque causes angular acceleration. It is the reason for the objects to start, stop rotating. So when you turn on the fan, there is a torque by the motor which starts rotating the fan. So again, there is a torque, a twisting force which is involved. Now, the other name for torque is also moment of force, like inertia was for linear motion, moment of inertia was for rotational motion. Force is for linear motion, moment of force is for rotational motion. But becomes a big name, no, moment of force. So they have given a new name for it. You can also call it torque. Okay. You can also call it torque. It is one and the same thing, moment of force or torque. Symbol is tau, that T with like an umbrella looking inverted J. So J looks like this. So this is like this. Okay, so inverted J kind of thing. That is tau, Greek symbol, alphabet. What is the value of the torque? Torque is measured by the position vector of the force from the axis. A lot of people write R as radius, or they imagine it to be the radius. Yeah, sometimes it is the radius, but it is not called as the radius. It is called as the position of that force, position of the point of application of the force with respect to my or axis, or the hinge about which the object is tending to rotate. Position vector, it's not the radius. Cross producted with the force. So if you just take the magnitude of it, if you just take the magnitude of the torque, it will be just R into F into sine of theta, because that's how cross product is defined. It is the product of the two vectors magnitude into sine of the angle between them. So if my position vector is here, my force vector is here, this becomes the angle between the two vectors. So that angle's sine, if you put, you get the value of the torque. Now, let's understand whether it makes sense. See, if theta is 0, meaning the force is parallel to R, that means my R is like this, force is also like this. So, if I apply the force parallel to R, the object will not even rotate. Think about it. If I'm pulling that object like this, why will it rotate? So, theta is 0, sine is 0, so no torque. But when this force is like this, then I'm using my maximum effort in rotating that object like this. So that case, theta will be 90, sine 90 is 1, which is also the maximum value. So that's why the torque will also be maximum when the force is perpendicular to the point of application vector. Is that absolutely clear, my dear students? Okay. Now, having said that, what is the unit of torque? And yes, torque is a vector quantity. I think I have put it somewhere, or no, maybe no. Okay, so I'll just put it out right now over here. Yes, torque is a vector quantity because you can see cross product over here. And yes, it is having a unit of Newton meter. It is also having a unit of Newton meter. Absolutely correct. Absolutely correct. Very good. Yeah, awesome. Guys, I also want to know, do you want detailed classes or do you want just question solving classes? Because yeah, that low attendance also is bothering me because at this point of time, usually we have very, very high attendance. And if the attendance is low, meaning that you guys want something else, so we'll change the series. It is not a big deal for me. So, you know, if you want detailed class, we'll do that. Or if you want PYQs, we'll do that. If you want just problem solving, we can do that. If you want something like an SCP practice, we can do that. If you want a mock test, it's too early for a mock test, we'll not do that. It's not like we'll do anything and everything. So whatever is right, we'll do it. Okay, so I would love to know what you want in the comment section after the session is over. Okay, not in the live chat, in the comment section. Okay, great. Now, having said that, the direction of the torque, use your right hand rule, as simple as it. So right hand rule, you have studied it in vectors chapter. You take your 4 fingers of the right hand, align it in the direction of the position vector, then slowly bend it towards wherever the force is. Your thumb will pop out. That gives me torque's direction. Okay. Over here also you can see R cross F. R is over here, force is over here. Wherever the thumb points, that is where the torque is. Now, when the torque is here, don't think the object is rotating there. No, no, no. Torque direction is just the direction of the thumb. It is just a representation. So if you place your thumb in that direction, automatically the fingers of your right hand will turn. That gives you the actual sense in which the torque is being applied, because torque can't be applied in a straight line. So it is just for directional representative purposes that we use that notation and that, you know, manner in which we you know, draw it. So if my thumb is in that direction of the torque, then the fingers of my right hand show me how the torque is actually twisting that body or applying the forces in order to cause that rotation. Okay? Yeah. All right. Perfect. Deshashri, Khatir, problem solving. Okay, fine. But I want everybody to put it up in the comments. Yeah, perfecto. Now, let's see some questions based on this torque calculation, of course. And by the way, by the way, if you want to measure the net torque, if you want to measure the net torque on a body, then that net torque is basically the vector addition of all the torques due to all the forces. So I can just say it is just the sum of all the torques due to all the forces, due to all the forces, due to all the forces on the body. And in a very special case, what happens is, in a very special case, what happens is, if that net torque happens to be zero and also net force is zero, and also net force is zero, then we say that the body, then we say that the body is in equilibrium. Then we say that the body is basically in equilibrium. Yeah, I hope this is very, very clear. Then we said that the body is in basically equilibrium if both the force and the torque are equal to zero. Only then. That means there is no net resultant left out. All the forces are balanced, all the torques are balanced. Only then we say that the body is maintaining its state in equilibrium. And for this, I have a nice question for all of you. Consider the following options and tell me which of the following are possible and not possible. Let's say we talk about force, net force is zero, and then net force is not zero. And in each case, we have torque is zero or not zero. So some of them are possible, some of them are not possible. What do you think? Okay, is the right answer to this. Explain the possibility, possible or not, possibility of each of these scenarios. Everything is net force and net torque. It's not a singular force or a singular torque. It is the net force or net torque. Let's start with the first one. Of course, net force is zero, net torque is zero. I think this is definitely possible because then it would mean that it is in equilibrium. Then it would mean it is in equilibrium, like at rest. If you are at rest, then nothing is there, no force is there, no acceleration is there, no angular acceleration, no torque is there. So everything is balanced. So definitely this is possible. Yeah. What about the second one? Force is zero, but torque is not zero. Net force is zero, but torque is not zero. Sounds a little confusing. Then when I ask you net force is not there, but torque is not there, again sounds confusing. But what about this? Force is also there, torque is also there. I think this is very straightforward. Definitely it is possible. Like for example, a body which is translating and it is also rotating. In such a case, what will happen? Like for example, there is a sphere or a ball and it is going down. So it is also experiencing a force downwards. It is also experiencing a torque. So that torque is changing its state of rotation and the force is causing linear acceleration. So definitely that body has some force and some net torque, and that is why it is changing its state. This is possible. Okay, now comes these two situations. Let's talk about this one. Force is not there, net, but torque is there. Initially, it feels impossible, but let me tell you, this is also possible. And I'll tell you how. Imagine this situation where you have two equal forces but in opposite directions. That is also called as the couple force. Couple forces or couple force. Couple forces like husband, wife, Pandu, Champa are similar but opposite. And what happens is because they are opposite, the force will balance, but since they are not on the same line or not on the same point, there is some distance of separation between them that causes the torque. So those two forces will cause a torque and it will rotate it. So imagine two forces like this, they will twist the body. Yes, they will not translate the body. So this is also possible. This is also possible. Clear? We have done fluid, Pranay. If I have not done, okay, I'll just see if the playlist is updated or not. Okay. Force is there, but torque is not there. This is also possible. A lot of people think this is not possible. Yes, this is possible. Just imagine something like, some square object is there, block is there, and it is just moving. There is no rotation. So only translation is there. Only translation is there. Only translation is there, but rotation is not there. So torque is not there. So this is also possible. So in fact, all are possible between force and torque. Is this clear? Very interesting question it is. It can be in statement-based question or maybe match the following, God knows. Okay, let's solve the question coming up on your screen. It's based on projectile motion combined with this. Let's see whether you can solve it. Just let me drink some water and come back. All right, let's do this. A particle of mass 2 kg is thrown with some speed at some angle. Find the torque because of the weight, that means gravitational force, about the point of projection when the particle is at the highest point. Okay, so let's draw the situation. Things will be very clear. Imagine this is our ground surface. The object is thrown from here and it goes along this particular path like this, and it reaches the highest point somewhere over here. So when it is at the highest point, when it is at the highest point like this over here, so what is this? When it is at the highest point, we have to figure out the torque because of the weight. Now this particular mass right over here at the topmost point, the weight because of it will be acting downwards. So this will be m into g. And I want to find the torque because of that about this particular point O. Now, if you notice, my position vector, technically speaking, is this one, which is over here. Okay, correct? Everybody with me? And I want to now do the cross product of R with mg to get the value of the torque. So if you now see, the angle between R and mg is slightly obtuse and all of that. It's becoming a headache now to even think about this problem. Plus, I do not even know what angle will this be, because yes, this is 90. How much is this? For that, I need some other calculation. It's becoming a headache now to calculate the torque. So what to do in such questions is that you don't really do, this formula, which is torque is R into force into sine of theta. The problem is, what is this theta? I do not know this. Plus this R, I have to find H range by 2 and then find it. So R also I do not. So instead, what you have to do is a simple trick, guys. See, when I showed you this formula, right? RF sine theta. Over here only I'll show it to you. Say for example, this is my axis, this is my position vector, and let's say this is your force. This is your force. Normally, you would say that the torque acting, magnitude wise is just, you can say, R into basically F sine theta. And when I say F sine theta, it means that you are taking the component of the force which is perpendicular to R. Because see, what happens is this, this line, when you extend it, this will become theta, this will become theta. Force will have two components. One component will be like that, and this will be F sine of theta, which is basically perpendicular to R, So this, you can think of the perpendicular component of the force. This you can think of as the perpendicular component of the force. This is one way of looking at the problem. Another way is, okay, same point, same position vector, same position vector, same force, but this time don't extend R, rather you extend the force itself, which is also called the line of force, and you split R into two components and only take the perpendicular R. Yes, this was your regular R. This is now your R sine theta, because this angle will be theta. This angle will be theta. Yep. And this is your force. Now your torque will be, instead of RF sine theta, it will be R sine theta. This part is now called the perpendicular arc, or the perpendicular distance on that force multiplied by the force itself. Just like work is Fs cos theta or F cos theta into S, two ways are there. Same way, torque is R into F sin theta or R sin theta into F. It feels mathematically it is the same. Yes, it is. But it is the manner in which you are interpreting it in physics. When you put F sin theta, you are taking the perpendicular part of the force to R. But when you put R sin theta, you are taking the perpendicular R. You are taking that R which is component wise perpendicular to the force itself. Both will give you the same result. So, using that concept over here in this particular question, I can see that this is my force. This is basically R perpendicular, which is nothing but range divided by 2. And you can see that your force is going along this line. Your force is going along this line. So now it becomes easy to calculate the torque about this particular point. So the torque will be R perpendicular into the force. R perpendicular is range divided by 2. Force is nothing but going to be mg. Range is nothing but, we have to find in terms of theta and all of that. So u square sine of 2 theta divided by g, but that 2 is also there, multiplied by m into g. So we have got the formula. Now it's just a matter of substitution. Is that absolutely clear how to solve this question? Okay, the catch is you don't have to find R because it is very difficult. I mean, you have to, lengthy it is. Range, height, Pythagoras, then theta also you do not know. Again, trigonometry. It's unnecessarily lengthy. Rather, what we do, you take the force, you drop a perpendicular on that force, you measure that distance, R perpendicular, and multiply it by the force itself. That makes the calculations very easy. Okay. What if the object is floating and it is not having force but has torque like the toy plane? So also torque will be there because of gravity. Irrespective of whether it is going in projectile or not, still torque will be there because of gravity, but maybe another torque is there because of the wind, and both the torques are cancelling out. So net torque might be zero if it is floating. But that does not mean torque is not there. Torques are there, but they are cancelling. Got it? So it doesn't matter whether they're floating or it's a projectile or just hanging, answer will be the same way. So you just have to now put up all the values. I think the speed value, everything is given to you. What is the speed value? It is 10. So put the value of u as 10, put the value of theta as 30, put the value of m as 2, g as 10. But I think gg will get cancelled from both the places, as you can see, this g and this g. So you will get the final answer right over here. The answer that you should get is, I think, around 50 root 3, if I'm not wrong. Yes, it is 50 root 3. Okay, so 50 root 3 Newton meter. 50 root 3 Newton meter. Is that absolutely clear? Yeah. Okay. Manish, like I said over here, if you go back a little bit, now the normal way of measuring torque by vector equation is cross product, IJK method, R cross F. But many times you don't need that, you just need the magnitude. So either R is given, F is given, theta is given, then so it is a very simple thing, R into F into sine theta, if everything is given. But if the diagram is given or you know the diagram, then there are two ways of dealing with the problem. First method is, you know how far the force is, where the force is and what the angle is. You take the perpendicular part of the force, which is F sine theta multiplied with R. That is one common way. But many a times it is not so feasible. How much is R, how much is theta, I don't know. But what you can do is, if you take the force and you drop a perpendicular on that line of force, you might know that value, which is R perpendicular. And if you multiply it with F, you will still get the same magnitude of the torque. So what we have done is, over here in this particular question, I know at the topmost point, gravity will be still acting down. Mg is like this. So this is the force line. On that you drop a perpendicular. I know actually the object will go and fall somewhere over here. So this would be the range. This would be range divided by 2. So R perpendicular is range by 2. Force is mg. So that's all I have done. force is mg, range by 2. Range formula in projectile motion is u square sine 2 theta by g. So solving it, you will get the answer. Is it now clear? Hello Adi, hi Manish, is it absolutely fine now? Shall we go ahead? Yeah, very good, excellent. Proud of all of you. Awesome. Let's go to another question where you are again required to figure out the torque. All these questions will help you, develop that skill of finding torque, because otherwise you will find lot of difficulty in solving complicated questions. There is some painter whose mass is 70 kgs standing on the top of a ladder of length 5 meter that leans against the wall at an angle of 60 degrees with the horizontal ground. Calculate the torque by the painter's weight about the bottom of the ladder. I feel it's a very similar question. Now, Manish, you should be able to do it. Think, imagine the painter's weight will act like this from the end of the rod, isn't it? So this is the force, this is the weight, the force, which is the weight, which will be nothing but m into g. About this point, I want to find out everything. So I will just drop a perpendicular over here. So if this length is 5 meters, how much will this perpendicular distance be from the axis? It will be 5 cos 60. Cos, why cos? Because adjacent side for a right angle triangle will be cos, opposite or far away side will be sine component. So this will be cos 60 is half, so this will be basically 5 by 2 meters. Now my job is done. I just have to figure out how much torque is there about this point. That force will generate some torque. So it will be R perpendicular into the force. Perpendicular distance is 5 by 2 meters. Force is weight. Now how much is that weight? 70 kg. So 70 into 10. 7 5s are 35. 35 by 2 is 17.5 multiplied by 2 zeros. So it will be 1750 Newton meter. That should be the answer. 1750 Newton meter. Okay, everyone? Absolutely clear? Yeah. Very good. Very good. Very good. Yes, you can definitely refer this video for any competitive exam, SMK. But yeah, we are teaching JEE stuff. So keep that in mind. Okay, very good. Perfect. Let's go now to another question coming up on your screen, and it is based on equilibrium concept. The diagram shown over here is of a rigid uniform meter long rod AB, which is held by two strings. So this is that rod. It is being supported by two strings so that it does not fall down. Now what has happened is the rod's mass is m, and you have attached a deliberate another mass 2m at 75 centimeters distance from one side, 25 from the other side. The tension in this string is how much? That is the question. How much is the tension in this string? Wow. Sir, what about the normal force? The normal force in that previous question will still be there, but torque because of that will not be there. Okay. See, even if you take normal force over here, tell me what will be the torque because of the normal force? It will be R into F. R is 0 multiplied by N. So the torque due to the normal force will not be there. Getting my point, Manish? Yeah. So I am finding the torque about this point. The point of application is the same point. So distance R itself is gone. R is itself 0. So that is why you will not get any torque because of the normal. Some might argue, sir, what about friction? Yes, friction will be there. Let's say it is like this. Even the torque by the friction will be 0 because friction is acting at that point only. So R is 0, frictional force is, torque is 0. I'm not saying friction is 0, I'm saying torque is 0. So that is how this works. Okay, let's go now to this particular question and solve it. Now, let me first start by drawing the free body diagram. Like there will be one tension here, there will be another tension here. This weight will be down. The scale will also have its own weight, but that will act through center of mass of the scale, which is at 50 centimeters mark. So let's start writing down the variables. Tension of A, this will be tension of B. The scale's mass, I believe, is given to be m somewhere. Yeah, the rod or the scale is m. So this will be mg. This is going to be 2mg. Okay. Now what do we do, sir, next? Observe. See, because the rods are suspended by those strings, it is in equilibrium. So that's my first observation. So everything is in equilibrium. So because of that situation, 100% net force is zero. So this tension and this tension together are balancing the weights which are acting down. So strictly speaking, tension A plus tension B upwards is balancing mg and 2mg downwards, which is coming out to be 3 times of m. So Ta plus Tb is nothing but 3mg. Okay, sir. Perfecto, sir. Now what next? Now what next? What is the next part? We have to find tension in string A. I don't know TB, else I would have solved the question, right? There was nothing in it. I don't even know what TB is. Oh, so how do I find TA? Sir, it is in equilibrium. So not only force, but even torque will be zero. Oh, yes, correct. But sir, about which point torque will be zero? It is not rotating only. So you take any goddamn point. How does it matter? You take this point, this point, this point, this point, any point you take, it is not rotating about any point. So torque is zero in general about every point. But then which point do I choose if I have so many options? I need to decide. Should I choose it randomly? Actually choose it conveniently, not randomly. See, what if I take this as the point to measure the torque? So look at it. Net torque about point B will be zero. So this 2 mg force is at a distance of how much? Just check this out. How much distance will this be? This will be 25 centimeters or basically 0.25 meters. Mg will be at a distance of 0.5 meters from this, and this will be at a distance of 1 meter from that point B. That's all I need. The distance is now observed. This 2 mg about this point will give a torque which is anti-clockwise. So there will be a torque due to 2m R into F. R is 0.25 into the force, which is 2 mg. But they are perpendicular to each other. This force and this distance R cross F, it is perpendicular. So sine 90 will be 1. So I don't have to put sine 90. It is understood. But that is anti-clockwise. This mg for this point is again perpendicular, and this mg will give a torque like this in the anti-clockwise because it will try to tilt the rod in the anti-clockwise direction. So again anti-clockwise, so I'll add it. So 0.5 multiplied by mg, but in anti-clockwise direction. This TA is at a distance of 1 meter, again perpendicular, so sine 90 is 1. But this tension will pull the rod like that in the clockwise direction. So clockwise means negative, I should put. So R is 1, force is TA, it is clockwise, is 0. So take this guy on the other side. So 0.25 into 2 is 0.5 mg. 0.5 mg is again over here. So 1 TA on the other side will just become TA. So TA will become 0.5 plus 0.5 is just 1. So just mg. That's it. The tension at point A is mg. So if you use that over here, you will get the value of Tb because that will be 3 mg minus mg, which is just 2 mg. So I can find both the values. Ta will be mg, Tb will be 2 mg. So 1 mg is the correct answer. Is that clear, everyone? How to find this? So whenever such equilibrium questions come, toppling questions, stable questions are coming, you take any random point, choose a convenient point and measure the torque and balance it out. One side clockwise you can take positive, anti-clockwise you can take negative. It's completely up to you. Maintain that till the end. Okay. Sir, what's my opinion about the present outdated Indian education system? Boys, even if I have an opinion, how does it matter, man? Like, I wish I could. I'm not a superman over here. I'm just a normal person. right? I have an opinion, but even if I say it, it is of no use. Still, students will do the same thing. Still, parents will do the same thing. Still, the system will remain the same. So, no point commenting. The main thing to break the system, the main thing to outgrow the system, to escape the system, is to study, come out, understand it, and make sure that you educate the people around you to not follow it. Because if I say it, then people will rebel and all those things. So I don't want to make those comments. Okay. Sigma Crash is enough, Charu. Don't have to watch this particular series because you are already enrolled in the Sigma batch. All right. Now let's talk about rotational energy and some pulley-based questions before moving ahead, which are based on torque. So first of all, torque and angular acceleration are related to each other, just just like force, the net force is the mass of the body multiplied by acceleration Same way, I can say that the net torque on a body is the moment of inertia, don't put mass, not acceleration, then angular acceleration. So this is the Newton's law, but for rotation, where instead of force you put torque, instead of mass you put moment of inertia, instead of acceleration you put angular acceleration. Those of you who have forgotten what is alpha, alpha is nothing but rate of change of angular velocity, which is expressed in radians per second square. Not just that, if you have some object like this and you know the tangential acceleration to be at, and this is basically r, then this tangential acceleration is basically alpha, angular acceleration, into r, basically. So it is alpha into r, that is the relationship between them. So these are some pretty standard relationships which you should definitely be aware of. Okay. Now, also keep in mind that because of this torque causing angular acceleration, whenever you will see a pulley with mass, this is very, very critical. Whenever you will have a pulley with mass, this is very, very important. What used to happen till now is that if when you are drawing free body diagram of the pulley, okay, doesn't matter, you will generally show T over here, T over here, and solve it, isn't it? But that will not be the case the moment pulley has a mass, because the pulley has a mass, it is rotating, okay? Once mass is down here, one mass is up here, it is going like this, the pulley might be rotating. So if it is rotating, it will definitely have some kind of angular acceleration. So in my Newton's law equation, moment of inertia of that pulley system is there, into alpha is there. So my torque can't be zero. This term over here is a non-zero entity. So my torque has to be present. Now, if the tensions are equal, what happens is, about this point, this tension will give clockwise torque, this tension will give anti-clockwise torque. Both of them will cancel out each other, which can't happen. That's why you will see one tension and another tension, both values will be different. And then you will see that this particular tension is at a distance of r, helping with the torque T2. It is helping with the torque like this clockwise. So I will just put r multiplied by T2 over here, and this tension over here, as you can see, it is against that torque, or against the alpha, sorry. This T1 will rotate this like this in the opposite direction, so it will give me negative torque. So minus r into T1. Not to mention r and the force, they are always perpendicular in such situations. So sine 90 will be 1, so you don't have to worry about the angle. So this is the equation. Whenever you will see pulleys with mass, the tensions on both sides are not same, rather they are different, which causes the angular acceleration. Very, very super critical. Okay. So Let's see one question based on that. Maybe you can figure it out. It's not two strings, it's just one string, but still you can do it. There is some cord, meaning wire or a rope of negligible mass, an ideal rope, and it is wound on the rim of a wheel. It is being wrapped, and you're pulling that other side with some force. The mass of the wheel is given, radius is given, it can freely rotate, that means no frictional torque is there. The wheel is at rest, you are pulling it with 20 Newton of force. The cord is unwound by 1 meter. What will be the angular velocity? The cord is unwound by 1 meter. What is the angular velocity? That is the question. Okay, let's think. What do we do? Just have this diagram. First of all, this force over here at this distance of r is definitely generating a torque. Is definitely generating a torque. So the torque generated is given by r into f into angle is 90, so sine 90. R is how much? Okay, let's just leave it for now. Just let's put RF. So that is the torque. So using Newton's law of motion in rotation, what do we get? Torque is equal to I into alpha. Torque is equal to I into alpha. Is that clear? Everybody? Torque is equal to moment of inertia into alpha. But the value of torque, I already know. R into F. Moment of inertia, how much it is? Moment of inertia, how much it is? Come on, guys. For what object it is? It's a wheel supported by negligible mass. So mass of the wheel is given, radius is given. I think we can take it like a disk. So the moment of inertia, I can put it as AMR square divided by 2, and this will be alpha. R will cancel. So from this, we will get alpha is equal to 2F divided by mass into radius. 2 goes with F, mr comes down, 1 of the r has got cancelled. Once we get the value of the angular acceleration, I think we can proceed ahead, because now the question is, what is the velocity after the cord is wound by 1 meter? Cord is wound by 1 meter, so it would have rotated by some angle. So I have an idea. If I know alpha, I think we can find tangential acceleration. That acceleration can help me find how much distance has this point moved. So that is the length of the cord which has been unwound. Oh, so tangential acceleration is alpha multiplied by r. So when I multiply this with r, I will get 2f by mr multiplied by r, which is 2f divided by m, is the tangential acceleration. Now let's use finally the kinematic equation. Displacement I know, initial speed I know, and I need to find velocity. I think we can do it. So final velocity is initial velocity plus acceleration into time. I was at rest. Acceleration is the tangential acceleration, which is 2f by m multiplied by time, but I do not know the time. So what do I do with it? No use. So how about using S is ut plus half a t square? That will be helpful. S is ut plus half a t square, but I again do not know the time. No. So the only option left is v square is u square plus 2a into s. Final velocity, I don't know. Initially 0. Acceleration 2f divided by m. Displacement is that length by which my cord has been unwrapped or unwound. Okay. From this, my velocity will be root of this entire thing, which is 4fl by m. From this velocity, I can find omega. Omega is v divided by r. So it will be 1 by r root of 4fl divided by m. Now you just have to substitute everything. So radius, how much is it? 10 centimeters, meaning 0.1, 0.1. Root over here, 4 is there, force is there, force 20. So put 20. Length is also there. How much length? 1 meter. So put 1 over here. divided by mass. Mass is basically 10. Okay, so put 10 over here. That's it. So 0, 0 cancels. So root of 4 is 2. So 2 root 2 divided by 0.1, which is 20 root 2. So 20 root 2 will be the angular velocity. 20 root 2 will be the angular velocity. Is that absolutely clear, guys? Yeah, everyone with me? Sir, will the L be changing constantly here? No, no, no. L, this is the final L. Obviously, this L at next instant will be different, but I'm interested after 1 meter, how much will it be? That was the whole point. So what we have done over here is we wrote torque is RF sine theta. From that, we equated it to I alpha. Moment of inertia, I took mr square by 2, assuming it is a disk. If it is not a disk, then it is mr square only. The 2 number will not come anywhere. Okay. If it's a ring, 2 number will not come anywhere. The answer will be slightly different. Okay. And then we start solving this particular question using kinematic equations. But for that, we first figured out how much is the acceleration. Acceleration is alpha r. I just gave that to you over here. A is alpha into r. So we have just directly used it over here. After that, what we have found omega. Omega is V by r, right? So substituting, we get the answer. Very good. All right. Sir, what should we do if there will be frictional torque? Then this torque will be different. So the actual torque external minus the frictional torque will be equal to I alpha. So that frictional torque should be given to you. Both the torques will be opposite. So I have put a minus sign. So that's all the difference will be if there is a frictional torque. Nothing great. Cool. Okay. Now, before going to the next question, we need to do the rotational energy part. Now see guys, when you take a body and you rotate it, each particle is moving in different speeds, different circles, different radius. So they all have different kinetic energies, right? You take any body, sphere, cone, solid cylinder, disc, ring, whatever. So they are all moving in circles. They all have some rotational energy, and we want to figure out what is the total rotational energy of that rotating body. The answer is simple. Just like in translational motion, kinetic energy of translational motion used to be half mv square. In rotational motion, what will it be? Instead of mass, I will have moment of inertia. Instead of velocity, you will have angular velocity. That's it. So it is half I omega square. That's all the differences. So for rotational energy, half I omega square. For translational energy, half mv square. So what if, sir, a body is rotating and translating both? So imagine there is a wheel or something like this, okay, and that wheel is moving with some velocity and some angular velocity. So the total kinetic energy is simply the kinetic energy of translation plus kinetic energy of rotational. So kinetic energy of translation will be half mv square. Kinetic energy of rotation will be half moment of inertia omega square. That's all. That's the only difference. Now, in some special cases, what will happen is if this is rolling, only in that special case, V will be equal to omega r. But if it is slipping, then V will be different from omega into r. So when it rolls means that point which is in contact will stay at rest. Every time a new point of contact will come, and that point will stay in touch with the surface and it will stay at rest. So in that case, velocity will be related to omega r, else it will not be related. So if it is related, you can substitute omega as V by r or V as omega into r, which will simplify it a little bit. So let's solve those kind of questions also. So mainly half mv square and half I omega square are the translational and rotational kinetic energies. So let's solve this particular question on your screen. There is a solid sphere which is rolling without slipping on horizontal plane. The ratio of the linear kinetic energy of the center of mass to the rotational kinetic energy is how much? Very interesting. Very interesting. Think the ratio of the linear energy to the rotational energy. Okay, let us put it on the next slide. So basically, they are asking what is the translational kinetic energy upon the rotational kinetic energy. Translational, we all know, is half mv square. Rotational, we all know, half I omega square. Half will get cancelled, m into v square upon I into omega square. Now it is the time for substitution. Be careful. Mass is mass, but clearly mentioned is it is rolling, so v will be omega r. So the moment you substitute this velocity as omega r, it will become omega square r square. Okay. Next, moment of inertia. Look at it. It's a solid sphere, so it will be 2 by 5 mr square. So instead of this moment of inertia, you are going to put 2 by 5 mr square. Okay. And then omega square also over here. Couple of things will get cancelled, of course, like you can see omega square, r square, m will got cancelled. Okay. So I am just left with 1 by 2 by 5, which is 5 by 2. So 5 by 2 should be the answer. 5 by 2 should be the answer, which is absolutely correct. Cool. So very simple ratio was asked. Translational by rotational. Translation you will use half mv square. Rotational you will use half I omega square. If it is rolling, you will use omega r is v. Else you cannot use that. It should be given to you. Very good. Okay. Sir, here where the axis of moment of inertia? The axis of moment of inertia for such situations where you are considering that rolling phenomena, you will always take this central axis. Okay, this central axis. The kinetic energy of rotation about center of mass. You will always take it about this center of mass. Okay, not at the point of contact, but you will take it about the center of mass. Okay, let's do the next question coming up on your screen. A body is rolling down an inclined plane without slipping. The kinetic energy of rotation is just 50% of the translational energy. The body is which kind? Three twisted question. This was asked in JEE mains. Solid, cylinder, sphere, hollow cylinder, ring. Okay, interesting. Let's write down what is given. The total energy is, no, the kinetic energy of rotation is 50% of translational energy. The kinetic energy of rotation is 50%, meaning half of the kinetic energy of translation. Okay. What is the kinetic energy of translation? It is half mv square. What is the kinetic energy of rotation? It is half I omega square. Half will get cancelled. What is the formula for moment of inertia? What is the formula for moment of inertia? For, oh, I don't know only what that word is. Oh, so I'll just put I. Omega, I'll just put omega. Half, I'll just leave it as half. M, I'll just leave it as it is, and omega v square will be there. Okay. Now I will do one more thing. I know if it is rolling, then velocity will be omega r. So this will be omega square r square. Omega square r square will be there. So omega square will cancel. So I will be mr square by 2. Whose moment of inertia is mr square by 2? It is either a disk or a solid cylinder. Both have the same formula. Solid cylinder or a disk. Hence the answer will be basically either a solid cylinder, solid disk is not, so I'll mark option B only. So these kind of questions have been asked couple of times in JEE, so you should be aware of it. Okay, very good, excellent, amazing, amazing. Now let's start angular momentum. Before starting angular momentum and conservation, I'll just give you a 5-minute break and we'll return. Just 5 minutes break, okay? Visible to all of you? Welcome back, everyone. Yes. So let's begin. Let's begin. So, yes, Kushal, like I said, this is a proper JEE high weightage unit revision. Okay. So, for those of you who want to revise the rotational motion, um, only the high weightage concepts, this is the lecture for that. But if you want to go from the basics, already the channel has marathons, or if you want problem solving session, this is the session you can look for just for application part. But yeah, there will be separate problem solving sessions exclusive just for mains, PYQs, and good level questions. We will conduct them separately, not now. All right. Okay. Now, uh, let's begin with the angular momentum concept. See, guys, now uh, linear momentum was talking about if you take a mass and you are throwing it with some velocity, that mass in motion has momentum. A body which is rotating has angular momentum. That's the difference. So just like you have linear momentum for translation, for rotating bodies, you have angular momentum or rotational momentum. Now, how do you calculate it? I will talk about it. But first, let's talk about the directional aspect. See, if you have a rotating body, if you know the direction of rotation, you take the fingers of your right hand and put it along the direction of rotation. The thumb will point in the direction of the angular momentum. Now, when the thumb points in a particular direction, let's say like this, and I say angular momentum is here, don't think actually something is going here, just like torque. So it is just a representation that angular momentum is here. So if you hold the thumb, the fingers move in the direction in which the object body is rotating to give you the sense of angular wise momentum. So the thumb is just for representation purposes only. Now there are two ways of calculating angular momentum. First is if you have a particle. Imagine a point mass, and that point mass is rotating about an axis. The point mass is rotating about an axis. So that point mass possesses an angular momentum because I know if that point mass hits something, gosh, it will transfer that angular momentum to that next particle. So point mass just even moving, need not be even rotating, even just moving possesses angular momentum. Just like if I have a pendulum and then there is a bob attached over here, as soon as it comes and hits something, it will transfer the angular momentum to the next thing. So a mass, which is a particle, has an angular momentum. Symbol for angular momentum is L. Angular momentum is m, scalar value. R cross V. R cross V is a vector product. So the final answer will be also a vector. Now what is R? Just like before, position vector. Of whom? The mass. Just like R was the position vector for force, here it is the position vector for the velocity. And V is the velocity itself. So imagine this is the point about which you want to measure the angular momentum. This is the mass moving with some velocity. This will be the position vector. So if you do R cross V, that will give you the angular momentum. R vector cross V vector will give me the angular momentum. Now what happens is when you take the cross product, you can also write the magnitude as R into V into sine of the angle between them. So that is also allowed. That is also allowed. Okay, perfect. All right, perfect. The Ekalavya test series is for 1999 only, my dear, but only on the Children's Day time it was for 999 rupees. So the offer is gone. So that's why it is now back to 1999. Okay, simple. Don't spam like this. Now, just like before, we can also measure angular momentum via two ways. Observe this now. Imagine this is R and this is velocity. This is your R position vector. Now, first way is you extend that R and you basically measure this angle, let's say this is theta, velocity will have two components. You take the perpendicular component, which will be v sine theta. Don't take v cos theta. Okay, don't take v cos theta, take v sine theta. This angular momentum about this point will be m is there, r as it is, into v sine theta. Now this v sine theta is nothing but the perpendicular component of v. That is one way to measure angular momentum. So you take the perpendicular part and you measure it. Very straightforward. But many times what you will need to do is you might have to extend this line like this and then drop a perpendicular on the line of velocity. Drop a perpendicular on the line of velocity. This will be r perpendicular. You can write the angular momentum as mass into, this will be r, actually this will be r sine theta, because this angle will be theta. So any side opposite to theta will be r sine theta. So m r sine theta multiplied by v. This r sine theta, like I said before, is your perpendicular r. This is nothing but your perpendicular r. That's it. That is how you can find angular moment. Let me show you a live demo of how you can apply this actually in one projectile motion problem only. Imagine this is the ground level. Imagine you have taken a projectile mass m and thrown it with some speed from over here. So what happens? Eventually it will reach somewhere and it will start coming down. And at some instant, it will be at the highest point. And we have to figure out what is the angular momentum at the highest point. Okay, the point is to figure out angular momentum at the highest point with respect to the projection, with respect to the point from where you have projected it. That is the question. So let's see how do we do it. First of all, at this point, mass I know, anyways the same mass is going to go here, so m is there. This velocity will no longer be u. Remember, in a projectile motion, two components, u cos theta will remain constant. There is no acceleration. Only vertically there is acceleration. So that will make that vertical component disappear. So highest point, the velocity will be u cos theta. Now position vector. The position vector will be basically this one. This is actually r. And if I try to do it by the traditional way, m into r into velocity into angle, I don't know angle, I don't know r, it's a headache. So instead, what I will do to measure my angular momentum is, I will write this as m into r perpendicular into my velocity. This will simplify the process by a large deal. What is r perpendicular? All you do is take the velocity, extend that line. Now drop perpendicular on this line. This is basically your r perpendicular. This is basically your r perpendicular. And guess how much that will be? Exactly the maximum height. Yes, you heard it right. It will be the maximum height. And what's the formula for maximum height? It is u square sine square theta divided by 2g. So just put u square sine square theta divided by 2g over here, and velocity is just u cos theta. My job is done now. It's just simplification. So m is there. U square into u is u cube sine square theta into cos theta, whole thing divided by 2g. That is the angular momentum. That's it. Is that absolutely clear? Is that absolutely clear, everyone? How you can use this technique? Which technique I'm teaching you? Same technique which I told you in torque also. Instead of splitting the force or velocity, here we are splitting position vector itself, which is the r perpendicular. Many times this is easier than the traditional approach of splitting velocity or force. Okay. on the line of velocity, drop the perpendicular. That perpendicular distance into velocity will also give me the angular momentum. So that's how you do it for point masses. It's a vector quantity. Unit is kg, meter square per second. Okay. But sometimes you might not have a point mass. You might have a body like a sphere, disk, rod, etc. In such cases, which are rigid bodies, each particle will have angular momentum on that body. So you take up all those angular momentums and you add them up. You get the total angular momentum. And no surprise, the value is I into omega. Just think about it for a moment. Linear momentum was mass into velocity. Angular momentum is angular mass, which is I, into angular velocity, which is omega. So exact replica, very similar, but different also. Like instead of mass into velocity being momentum, I, which is moment of inertia, into angular velocity, you are getting the angular momentum, but not for point mass, for a big rotating body. Okay, anything, it could be a sphere, disk, anything. So I value, you already by hearted it, you know how to find it. Multiplied with omega, that is the moment of inertia of a big rigid rotating body. So how do we use this? But before that, let me just show you how to calculate it. For example, imagine a disk of mass 4 kg and radius 3 meter rotates at 10 radians per second. What is the angular momentum? If this is the question, angular momentum, we know for any rigid body is I into omega. It's a disk, so moment of inertia is mr square by 2. So into omega, mass is 4, radius is 3, divided by 2, multiplied by omega, which is basically 10. 4 by 2 is 2, 3 square is 9, the whole thing into 10. So this will be 180 kg meter square per second angular momentum. Okay, so very simple and straightforward to calculate for any kind of rigid body, whether rod, disc, cylinder, anything. Now, where do we use this? We use it for many purposes, calculating basically for angular momentum conservation. Now, this is a very interesting example where you might have seen it in a dance or in a sport activity or even in a science experiment where you are on a platform like a merry-go-round or a rotatable turntable, and you are given a gentle push. So you start rotating and then you are asked to move your hands away or then bring it close. You see a very big change in your angular speed. Now, why is this happening? The reason for that is something called angular momentum conservation, and that happens because of this between relation between torque and angular momentum. Very interesting thing. Just like force is rate of change of momentum, just like our force used to be rate of change of momentum, here we have in rotation, torque is rate of change of angular moment. Very important relationship. Torque is rate at which angular momentum changes. So I can put it up in words. Net torque is the rate of change of angular momentum. Rate of change of angular momentum. Is that absolutely clear? Just like F is dp by dt, torque is dl by dt. What happens because of this is that if the net torque on a system or a body is 0, that is torque is 0, therefore what will happen is dl by dt will be 0 and the derivative is 0 means it is a constant. Therefore, L is going to be a constant, which means angular momentum is conserved. Angular momentum is conserved. Very, very important thing. If torque is 0, angular momentum is constant. This principle is also called as the law of conservation of angular momentum. Law of conservation of angular momentum. Law of conservation of angular momentum. If the torque is not there, then angular momentum will remain conserved. How do we use it in this particular example? Now think, here this person was asked to rotate. Once rotated, once pushed, there is no torque. The person is rotating by himself or herself. So there is no torque, so angular momentum should remain conserved. Now this person is a body, so has a moment of inertia and also has omega. And that's exactly what happens over here. See, when your hands are far away, all the particles are going in big circles. R is big, so moment of inertia is large. But when you bring your hands close, all the particles are rotating in small circles, so moment of inertia is small. What is the formula for angular momentum? What did I just tell you? Angular momentum for big bodies, what is it? It is just I into omega. I just made you calculate it also, right? I into omega. So it means if I is more, omega will be small, and if I is less, omega will be large. In order that L, which is angular momentum, is same as before. So when my hands are far, moment of inertia is large, small angular velocity. But the moment I bring them close, moment of inertia reduces, so I'll start rotating really fast. That is the principle of conservation of angular momentum. It's very interesting. But keep this in mind that although angular momentum is conserved, it is possible that energy may not be conserved. Okay, energy may not be conserved in all the cases. So for energy conservation, you have to use work per energy chapter. Kinetic plus potential is constant only when non-conservative forces are not doing work and all of that, like friction, viscous force, drag force, normal tension. If they are not working, only then energy is conserved, else it will be not. Okay, so keep this in mind. Let me show you some simple examples so that you guys get a confidence. Let's start with this. There is a ring, radius r, rotating with some speed. Now, what happens is, two point masses are attached on the opposite ends. The ring will now rotate with what new speed? Very simple question, although it came in JEE. This is a ring, before versus afterwards. This is the axis of rotation. This is the axis of rotation. Now, the ring had a mass of m and radius of r. Okay, and if two objects of mass m are attached to the opposite ends, so one end over here, one end over here, 2 point masses, opposite ends, this is r and this is r. All right, perfect. The ring will rotate with what new angular speed? So earlier the angular speed was, I think, how much? 2 radian per second. What is this new velocity going to be? Now, when you put those masses, you're just placing them, you're not pushing them like this or stopping them. So no torque is given in this situation. So external torque is 0. So angular momentum is constant. So what is the angular momentum before versus afterwards? Let's see. First, moment of inertia into omega, which is 2. Moment of inertia of a ring is just mr square. Later on, moment of inertia is not just of the ring, plus also the point masses. So small m into r square, but there are two masses. And this whole thing into omega. I omega is I omega. I's are different. Now, please be careful. This is actually capital M. I should put it like capital M or else it looks similar to this. Okay. R square is getting cancelled. So, 2 capital M is capital M plus 2 small m into omega. Therefore, omega will be 2 capital M divided by M plus 2 times of small m. Is that absolutely clear? Yes. Awesome. Awesome. Perfect. So this should be the answer, 2 capital M by M plus 2M. That is option number C. Yeah, perfect. There you go. Amazing. Now, a similar kind of question has come in JEE 2021, but the question is slightly twisted. They have asked that if you have two disks, different inertias, and they are rotating with different speeds, and then they are brought together, like two different speeds are there, and you bring them together. Now they will rub against each other. Finally, they will rotate together, and in that process, some frictional loss will happen, and because of which kinetic energy will be lost. How much is that loss is the question, and four options were given. So let's visualize this diagram first. Okay, so we have, this disk over here and another disk over here, maybe like this. Two disks are there before, and then you place them over each other like this. Earlier, this was omega 1, this was omega 2. Now they will rotate with one common angular speed. In this process, because there is no outside torque, they were just placed. Whatever is there is internal, so no torque is there from outside. So torque is not there. So angular momentum is constant. Therefore, original and final should be the same. Now they are rotating with same speeds, different speeds, omega 1 and omega 2, and they are brought in contact coaxially. Okay. So initial angular momentum, if you ask me, it will be I1 omega 1 plus I2 omega 2. Final moment of inertia will be I1 plus I2 together into a common angular speed. So omega will be I1 omega 1 plus I2 omega 2 whole thing by I1 plus I2. That's what it should be. This is my final angular speed. And that is not even the question. The question is something else. Question is, what is the loss of kinetic energy? Oh, so originally there will be some kinetic energy. Finally, there will be some energy. The difference will give me the loss. So the loss of kinetic energy will be, first energy will be half I1 omega 1 square plus half I2 omega 2 square minus half new moment of inertia is I1 plus I2 common angular speed, which is omega square. I just realized I don't think I was audible. I'm so sorry, guys. My bad. But I hope you saw me solve this. It was just a mechanical procedure what I did from here. So I'll just explain and give you a recap. Earlier, the two disks were not in contact. Their angular speeds were given. Final angular speed, I assumed it. So when it is in contact, it will have new angular momentum, new angular speed. So using conservation, I omega will be constant. I found out the new speed. Use this to find the loss of energy. This is this guy's energy. This is this guy's energy minus this energy. But omega, we had found out before, which was this whole term. So I substituted omega over here. Things will get cancelled, but since I1 plus I2 was not there here, I have taken LCM and simplified this. It looks like, a lot of nonsense is happening, but it is actually not that difficult when you sit with the pen. And then you see it simplifies to this. I was saying, please remember this formula because in the JEE exam, this pattern model has repeated multiple times on conservation because you will waste otherwise a lot of time, solving this. Okay, cool. So that was that particular question, and we are done with today's lecture where we have solved rotational motion, high weightage, all the topics which have consistently come in all the JEE mains papers. If you do this much, there is a very good chance that you will be able to solve almost all the questions from rotational motion. So make sure you are watching this lecture and solving more questions like this by yourself. But since not everybody can be motivated, if you want to take help of more modules, more material, BPPs, etc. Like our amazing students have been taking, in the Sigma batch, and I'm really happy. My Sigma batch students are extremely delighted every single day to attend every single class. Just now also, I got some messages, I was reading them, replying to many of my students. So thank you so much, guys, for loving these lectures, and thank you for liking this video and subscribing to the #1 JEE English channel. This was your Captain Shreyas signing off. Bye bye. Take care.